start the recording.
Yeah.
Okay. So yeah, thank you everyone for joining. Today we have a nice colloquium speaker from the University of Bonn, Dr. Athira Menon. Athira obtained her PhD how many years ago? In 2017 at Monash. So she is one of our extended family, and since then she has done a postdoc at the University of Amsterdam, and then she has recently become a Humboldt Fellow at the University of Bonn. However, she is still working from India, and she's going to finally get into Bonn next month. So she's going to have a big transition again. So anyway, today we are going to, she's going to tell us about the long stellar union of massive contact binaries. So Athira, please take it away.
Yeah, thanks Rio for the introduction, and I can't tell you how happy I am to actually be able to give a colloquium now as an external speaker at Monash. I have great memories of having studied there and have been part of the family when it was called MOCA 5 years ago. So very happy to do this talk. I wish I was there in person, but given the circumstances, also happy to do it from India. Right, so I've always been fascinated by stellar mergers. In fact, in my PhD, I investigated the progenitor of supernova 1987A from the stellar merger hypothesis. And that fascination has continued through my postdocs as well in Amsterdam and now through the Humboldt Fellowship. So today I'm going to speak about witnessing, actually observing a stellar union in real time. And that is via these massive contact binaries. Let's just start right away. So of course, we are very familiar with this zoo of stars in the universe. We have single stars, you've got binary systems where you've got two stars going around each other, which are gravitationally locked. And then of late, we've been discovering systems with tertiary companions, triples, quadruples, etc. What's important for massive stars is that the higher the masses of a star, the likelier it is to be found with a companion. So the fraction of massive stars in binaries can go up to 100% for the most massive stars that we have observed in the local universe, which includes the Milky Way and the Magellanic Clouds. We also find, in fact, and that's the plot on the left in this screen here, that the probability of observing these massive stars in closer orbits is higher than those in wider orbits. So that might indicate that these stars were in fact born in closer orbits. That is something to consider. So we can therefore predict that most massive stars will interact in their lifetimes. Now, on the left here is actually an understated looking pie chart, but it's quite a seminal one. Coming from the work of Ugsana and other authors in 2014, where you see the fraction of stars that are expected to interact in different ways. Almost 70% of them 70% of massive stars are expected to undergo some sort of exchange of mass during their lifetimes. And that could be via different ways. This one here is a cartoon of a common envelope phase, one of the least understood stellar phenomena that could leave you with two stars that are retained, or you might end up having both of them merge through the common envelope phase rather. Or you have something like this, a stripped star that donates matter to its companion, leading to the spin up of the companion. So this diversity of massive stars, we do observe them, and we expect that an interaction is a necessary phenomenon they will undergo during their lives. Now, it is absolutely crucial that we understand the dynamics of stars while they're alive, in order to explain the stellar corpses that we are obtaining data for in the last 5 to 6 years, what with the LIGO, advanced LIGO, and LIGO Virgo as well. And also the variety, the diversity of supernovae that we observe through different facilities, the ZTF, the Zwicky Transient Facility. So it's very, very essential that we are able to constrain the lives of interacting binary stars in order to explain this, the deaths of stars and the diversities we observe in them. And this is more so important with the upcoming advanced surveys, especially the LSST, which is expected to observe about 1,000 supernovae a night. So are stars still interesting to study? The answer is yes, they're absolutely relevant to study. And there are many fundamental phenomena we actually aren't aware of. So there are equivalent surveys, observation surveys happening for massive stars as well. One of the most complete ones is the one that occurred for the Tarantula Nebula in the Large Magellanic Cloud called the BFTS survey, which is to date the most complete and unbiased study of massive stars in a given region. There are other surveys that are still processing their data. So all in all, both of these things must go hand in hand. Sorry, I can hear some sort of, someone's mic turned on. It's a bit, yes, thanks. So both of these things should go together, understanding the lives of massive binary stars, along with looking at the deaths, their final fates, which we're getting data for as well. One is absolutely necessary to explain the other. So of that pie chart that I showed you earlier, as I mentioned, stellar mergers are the least understood stellar phenomena. And why that is because we can't actually observe it. We do have evidence of them having occurred, for example, through my personal favorite, The Origin of the Progenitor of 1987A, to explain the rings, the triple ring nebula around the central remnant there. Perhaps magnetic stars, stars or progenitors of objects like Eta Carinae, superluminous supernovae, even long duration gamma ray bursts. All of these are expected to most likely have come from stellar mergers, but the phenomenon of the merging phenomenon itself is something we really don't have much of an idea about. Now, not all closed binary stars will end up merging. The fate of closed binary stars also end up in leading to double black holes or double neutron stars. So we must understand the borderline between stars that will end up merging to form these exotic stellar phenomena and objects that binary systems that must avoid merging, but be close enough to have mergers of dead stars, black holes or neutron stars. And the line between that is quite thin. We don't really have a study that investigates the impact of metallicity and what might be the progenitors of these kind of objects in detail. There are separate studies, but not one that is quite comprehensive. This is still required and wanting in this field. So as I mentioned, one of the most debated, or perhaps still something that people are still working on, and also in Monash, in fact, is this common envelope phase, which is the phase just preceding the stellar merger. There have been quite a few 3D simulations that have been done over time, and we're still just grappling with what it actually is, along with all the uncertainties involved in this period of time. So we, of course, haven't observed a common envelope phase occurring in real time because the phenomenon is of such a short duration. But we do have quite likely the phase just preceding a common envelope phase. And in massive stars, that would be a contact binary, something that we have observed. Unlike a common envelope, this here is a system which shares a common equipotential surface, but the two stars maintain co-rotation, and it could be a stable configuration for millions of years, which is why we observe them in the first place. The poster child for massive contact binaries is this video that was released by ESO. This is VFTS 352. These are two stars which have 30 solar masses each. So in total, this is a 60 solar mass system. It's really interesting because we don't know whether to call this one star yet or two stars. And so modeling them is a challenge in itself. Another clue about the link between a contact binary and a merger is this object here, V1309 Scorpy. This is a low mass. This was a low mass contact binary, actually. So they've taken light curves from over 6 years, and they found out that indeed this was a contact binary. And then there was an outburst, which you can see in this magnitude diagram over here. This huge outburst, which is attributed to the merging phenomenon itself. And I would highly recommend you read the papers for this object, because this is the only merging that we have observed or indirectly observed rather, through the signature of the luminosity of the system. And a lot of dust was observed around the central remnant as well. So this is perhaps the only clue we have of a merging phenomenon, and it's linked to a contact binary, albeit it is a low mass one. Okay, so how does one actually observe a contact binary? So when it comes to binary stars in general, we have visual binaries, we have eclipsing binaries, and spectrometric binaries. These are the main three categories. An eclipsing binary, one in which the light curve shows a uniform deviation in the brightness, it's the same cyclical deviation, that is expected to be the origin of a contact binary. Only a contact binary will show you that. If it is a semi-detached or a detached one, you would see difference in the brightness over time. Not in the case when you see a contact binary. So that is the key signature of detecting contact binaries. There are low mass equivalents. When I say low mass, the total mass of the system is about 2 or 3 solar masses at most. And we have thousands upon thousands of data for low mass contact binaries, but only 40 or so from the massive ones, because they're so short-lived anyway, of which we only have the stellar parameters derived for 22 of these massive contact binaries, something that we will be using in the work that I will show you ahead. Okay, so contact binaries are not only exciting because they might lead to a stellar merger and then the whole plethora of objects that can come out of it, but also to probe fundamental stellar physics as well. Things like orbital evolution in such a configuration, this peanut-shaped structure that we saw, tidal deformation, rotational mixing. We, in the simplest state, in a single star that's rotating, we expect meridional currents to be the primary drivers of rotational mixing. What would that be in such a weird configuration? Don't know. The possibility of angular momentum loss, and then the formation of disks around these objects, because they could lead to an eventual merger. And of course, most importantly and the least understood, is the transfer of energy in a shared radiative envelope. So that last part there is something we are absolutely clueless about so far. In the case of models of low mass contact binaries, low mass contact binaries share a common convective envelope. We do have models for those, but we have no idea how energy is transferred in a shared radiative envelope. So any models that we have don't deal with energy transfer in the shared envelope. That's important to remember. So on the left, I have put down all the stellar parameters that we have in hand with which we can compare with. These are the observed parameters for some of these systems. And as I mentioned, we'll be comparing the theoretical distributions with this observed data. Right, so how do we actually model contact binaries? I am an expert in 1D evolution, so I'll be using MESA to perform the calculations. And MESA at the moment already has a prescription called the contact scheme to deal with the evolution of contact binaries. This was in fact put in by Pablo Marchand during his PhD thesis sometime in 2015 or 16, later implemented into MESA itself. It is quite a simple scheme, but it works, and it's based on some physical realities, let's say. So the way it works is, as I mentioned, see, contact binaries by itself, they're complex. In 3D, they should be modeled, but it's not been done yet. So we have to make do with 1D models, and we have all this data to compare with anyway. So by comparing the disparity between the models and the data, we can try to figure out what might be the missing physics that we need to put in. This is just how we work in this field anyway. So what you see here is a cartoon of a binary system with its Roche lobes and then the shared envelope on top. And how the contact system is treated is that when both stars have their radii exceeding their respective Roche lobe radii, the mass transfer rate from the more massive star to the less massive star is adjusted to follow a certain analytic expression that Pablo derived in his thesis. And that is the expression that I have put over here. We don't need to go into too much detail. It is not a very complicated expression, actually. It just shows you that the relative radius of one star is adjusted with respect to the relative radius of the other star. And the mass transfer rate is also adjusted in order to maintain that relation. So what you see here is that when Q, which is the mass ratio, when that equals 1, then the scheme demands that the relative radii of both the stars must become equal. So accordingly, the rate of mass transfer also drops considerably as Q approaches 1, right? Because that's how you can maintain the relative radii of the two stars to be equal. So that's how the mass transfer rate is implemented. As I mentioned, energy transport in the envelope is completely ignored. And this is also assuming a conservative mass transfer. So nothing's actually lost from the system. Now, a merger that, or rather a common envelope phase is expected to occur when mass leaves the L2 Lagrangian point, which you see on the right side of the diagram. And this in itself occurs when at Q equal to 1, that is when the stars equalize in mass, the radius of the less massive star is 1.32 times the Roche lobe radius of the second Lagrangian point. And that is when we expect L2 overflow to occur, which is where we end our calculations because we don't know how to model the common envelope phase in 1D. Couple of things. Yes, Ilya. Hi.
Hi, Athira. Sorry, I hope you don't mind the interruption. I had a quick question.
No, not at all.
You didn't actually write down an expression for the mass transfer rate itself. So I was wondering, can you give us a sense? Obviously, the mass transfer is adjusted so that gradually you move towards equal masses in this over-contact binary configuration. Can you give us a sense for roughly how long it takes to get there? I mean, I realize that it slows down eventually, but let's say to get to within, a few % of equal masses, if you started with unequal masses, are we talking about a tiny fraction of the main sequence lifetime or a significant fraction of the main sequence lifetime?
Thanks. That's actually great because that's what's going to come in the next slide. So you'll actually see the evolution of the system with these parameters. I'll show you that shortly.
Thank you.
Yeah. Okay, so a couple of things that we don't consider in this contact scheme. I already mentioned energy transfer being one of them, but also tidal deformation. As you can expect, of course, these systems are tidally locked, but then that can also lead to some compression as well. So would there be any mixing originating because of tidal tides? It's something that Ben Hastings recently did some work on this, and he's also from Bonn. But that seems to be occurring only for the highest masses in a given grid of models. So I believe the mass of the primary and the secondary must exceed 50 solar masses in order for tidally induced rotational mixing to take place. So, but for the models that I'm building here, this is not something that would play much of an effect. We will, of course, be able to use this model to derive the orbital evolutionary parameters, so the mass ratio and the period, something that we can obtain from these models to compare with the data. Rotational mixing is as it is for a single rotating star due to meridional currents, nothing else that's implemented here. Angular momentum loss is also not considered in the evolution. So these are the things that we can, the only two things that we can say that we can have some say in fact, for the contact binary parameters are evolutionary parameters from the orbit and something from rotational mixing that will impact the surface abundances of this system. Okay, credit to Pablo Martin there as well. Okay, so the work I'm going to now describe is my own, and that's what I've been doing for the past few years. Part one of the paper is published, and that's exclusively for the Magellanic Clouds. And here I have just listed how I build the grids of models that I have used to compute the theoretical distribution of the orbital parameters, right? I consider a grid based on 3 initial parameters. One is the mass ratio, so that goes from 0.6 to 1. Then the total mass, which is M1 plus M2, spans from 20 to 80 solar masses. And the initial period is from 0.6 to 2 days. Now you might ask why I have considered this range, and that's to keep in sense with the observed systems, which also show these parameters within this particular range. So this is informed from the observational data of massive contact binaries. I consider the grids for 3 initial metallicities, the LMC and SMC, which are half and 1/5 of solar, and the newly computed grids, which I'll be presenting today for the Milky Way or the solar metallicity. I use a MESA, of course, to compute the models, assuming that the mass transfer is conservative, and initialize the evolution right from 0H main sequence and assume that the stars are tidally synchronized, which they will be at these short orbital periods. And the models are terminated just prior to overflow from the L2 Lagrangian point or when they leave the main sequence. So that's how the model grids are constructed. Now, coming to Ilya's question here, just see, do you see my pointer on the screen?
I don't.
Oh, it's a pity. Let's see. Let's try to some slopes.
Oh, now we do.
You do?
Oh, sorry. When you were not in the
full screen
slideshow mode, yeah, when you were in the other mode, we could see the pointer.
Okay, so please bear with me for this one. I'm just going to use my pointer here because I need to explain what's happening. Okay, so there are 2 main ways in which a system evolves when it enters contact. This is one type of evolution that I'm going to show you here. The initial parameters of the system are the following. The total mass is 26 solar masses. The initial mass ratio is 0.8, and the initial period is also 0.8 days. This is the HR diagram over here, of course, on the left, and the solid line shows the evolution of the primary. The dashed line shows the evolution of the secondary. The system enters contact around point A, and then is expected to enter the common envelope phase at point B, where the evolution is stopped. So what you see here on the right are the evolutionary parameters themselves. You can see that very close, just after beginning their journey from the 0H main sequence, within 10,000 years, the system enters contact, and there is an immediate exchange of mass on a rapid timescale, the thermal timescale, and thereafter it slowly drops down to lower and lower values in the mass transfer rate. And that, I think Ilya would explain how this is implemented, or how the mass transfer rate pans out during contact. So you can see also in the second panel here, the exchange of mass. First, it's rapid on a thermal timescale. After that, the more massive initial secondary transfers mass, and slowly, but actually rather quickly, in fact, I would say within 1 million years, the stars equalize in mass. remain in contact, do not detach until the end of the evolution. So for the total lifetime of the binary just before merging, most of it is spent in contact. The system remains in contact and is expected to eventually merge. So that is one type of evolution. Let's see here. Okay. So now if you'd like to see the evolution of the period and the mass ratio, as I had mentioned, the system equalizes in mass quite rapidly, and the period keeps shrinking. We are assuming a conservative mass transfer, and so by the law of conservation of angular momentum, we expect the orbit to keep shrinking. When mass is transferred to the more massive one, the less massive star. So that keeps shrinking, and when the system starts out, it has 0.8 days, and this goes down to roughly 0.7 days or so before it finally merges. Now, the second type of evolution is a bit different. It's the same system, except that the initial period is now changed to 1 day. So just with the difference of 0.2 days in the initial period, the evolution also is considerably different, right? You can see, in fact, that the system enters contact twice. If you look at the HR diagram here, between points A and B, it's a thermal contact. And you can see it side by side with the panels on the right. There's an immediate exchange of mass on a rapid time scale. Then the system detaches. And then one star begins to transfer mass to the other one. But that continues to be the initial primary. That is the star here, which started out with 14.2 solar masses. It exceeds its Roche lobe. So the less massive star now donates mass to the more massive one in a semi-detached configuration. What that means is that the period now begins to get larger, the system widens, the mass ratio deviates much further from 1, and then once both stars again enter contact, that is, both of them overflow their Roche lobes simultaneously, mass again now is exchanged, but now from the more massive star to the less massive one, leading to the period getting smaller and the mass ratio also quite quickly dropping towards Q equal to 1. And also this system eventually is expected to merge, but the net contact timescale in this type of evolution is only 1/3 of the total main sequence lifetime as a binary. So these are the two main types of evolution followed by models that enter contact. So the main takeaway message is that from the grid of models that we've computed at the metallicities that we've considered, the majority of nuclear timescale contact binaries will equalize in mass before they merge, right? Now I'm going to just show you what happens by looking at some slices through the grid. We need to see, how does the duration of the contact timescale, the contact phase, vary when we consider different initial parameters. So to start with, this diagram here is the slice of the grid which starts off with nearly equal masses, 0.95. On the y-axis is actually the period, the initial period, and on the x-axis is the total mass of the system. Mainly everything that is not marked with a star, the green star, all those systems are expected to merge. So in this case, systems from roughly 1.5 to 2 days with masses over 20 or over 30 rather, to be absolutely sure, are all expected to merge. What's really interesting though is that the duration of contact it goes up to 11 million years for the system that starts out at 0.8 days in this case. And of course it belongs to the least massive binary because in general they have shorter timescales anyway of life in general. So that's really interesting that this stable configuration can sustain itself for 11 million years. Let's go back to this. But if we take the grid with the most unequal masses to start with, the picture is somewhat different. More number of systems are expected to avoid merging. That's just my dog. More number of systems are expected to avoid merging across the masses that are considered in the binary model here. We do face somewhat more convergence errors when we have when we begin with unequal masses. But the trend remains, right? That the majority of contact binaries which are alive over nuclear timescales will end up merging. That's just to show you slices of the grid to see what's happening in there. Let us now see what happens when we compare our models with observations. To give you an overview of the observed contact systems here, I have just put them on an HR diagram. All the colored points there are actually the primary and secondaries of different contact systems. On the left are from the Magellanic Clouds, and from the right are, and the ones on the right are from the Milky Way. For reference, I have overplotted some single star tracks that are computed with different rotation velocities. And that's just to give you an idea where these systems lie. One can see quite immediately that most of the observed systems are very close to the zero-age main sequence, and especially so in the Magellanic Clouds. So what could that tell us? Either that most of these systems have already merged, or that they are quite newly born, so we're just observing them right now. What is interesting also is that from the observational side, we call all of these contact binaries. And as I mentioned, the signature is the light curve, the eclipsing light curve of the system. But there are significant errors on the actual status of a contact binary. Systems that are approaching contact, that is, they're not quite in contact yet, are also dubbed as contact binaries. That means there is enough room for error for most of these systems that you see here, in fact, for not really being true contact binaries, but only just approaching contact. And that can actually significantly impact the distributions we compute as well. More about that in some time. So let's see how we actually construct the theoretical distributions. One does this by actually considering the priors on the parameters that we're constructing the distributions for. So the priors would mean we assume that the mass ratio, initial mass ratio is flat in Q. We assume that the total mass of, well, actually the mass of the primary, not the total mass. The mass of the primary follows the salpeter IMF, and that the periods are, initial periods are flat in log P. Along with this, to construct the histograms that we're going to soon see, we also consider the time spent by each model in the grid in contact for every bin in period, mass ratio, and the total mass. So combining these two together, we can get an idea of what must be the current, the present day distribution of contact binaries across period, mass ratio, and the total mass. Okay, so this is a histogram distribution you're going to see recurring over the next slides. On the y-axis is just the value of normalized probability for observing the period in the first panel, the mass ratio, and the total mass in the final panel. What one immediately sees again is that the Q=1 value, that is equal mass contact binaries, dominate the prediction that we can get from theory. Is that really true for the observed systems? We will come to see shortly. But the main parameter that is impacted by changing the metallicity is in fact the orbital period. With increasing metallicity, the distribution of the orbital period shifts towards higher values. From 0.9 days is the peak of the value of the Milky Way to 0.65 days in the small Magellanic Cloud. But otherwise, everything looks more or less similar. So here you have the predicted distribution. Now, using the same 1D histogram, we just constructed 2D histogram to see how the period goes with the total mass of the system, and on the right with the mass ratio of the contact binaries. So these are true contact binaries, which means that I have constructed these distributions for models only when both stars have R over RL, which is the radius of the star over its Roche lobe radius when it exceeds the Roche lobe radius, when it's greater than or equal to 1. So this is the distribution of true contact binaries. You can see on the left panel, as one would intuitively expect, that the lowest mass binaries do dominate the distribution, and that the periods are expected to be less than 2 days for that chunk over there. But the observed points, the observed systems are all over the place, right? In particular, the scatter of points for the Milky Way is quite extraordinary. It doesn't seem to follow any particular correlation or trend, and that is quite mysterious, actually. We are, as I will show you later, not able to reproduce the Milky Way scatter really well. But the red points there, which come from the large Magellanic Cloud, there is a tighter correlation between the mass and the orbital period, and the mass ratio. In general, we see that the more massive systems are wider, something that we can actually also see from the 1D histogram that is constructed. And that's something we can actually see in the plot here as well. We find that the widest binaries must come from the more massive stars. There are only 2 points that we have from the small Magellanic Cloud. Both are plotted there as well. But what's really interesting is the plot on the right. If you look at the pink boxes, the pink rectangles that I've put there, there are 7 data points that fall on them. Those are the only true confirmed contact binaries that we are certain they are quite deeply in contact, right? And what we see is that for 5 or 6 of these systems, they do have equal masses. So could that mean that the other systems are not truly in contact, but near in contact? That is something that the observers will have to answer. But let's dwell on that a little bit more as we go ahead. But prior to that, an important question to also consider while building these distributions is that you see that the distribution here excessively favors the lowest mass binaries, and that's quite obvious. That's what would happen. But is that quite right? Should we be building distributions according to the masses of the stars themselves? So should we place filters on the total mass of the binary in order to construct realistic theoretical distributions? So then I performed an exercise where you can see in the middle panel, I only consider systems that are born with total masses over 30, followed by total masses over 40. And while the Q distribution, the mass ratio distribution, is not affected much, the periods are in fact quite nicely altered. That again links back to the fact that for the more massive systems, the orbital periods are also wider for contact binaries, and especially so for the Milky Way grid. Let us see how that translates to the 2D histograms again. Here we only consider systems which have total masses over 40. And you can see that in fact it looks a little bit better. You do reproduce some of the unequal mass contact binaries in this case. But still there's an overwhelming block for Q equal to 1 that cannot be rid of even by placing a filter on the total mass. But the oddest of the lot are the widest binaries in the system. Here you can see 3 arrows that I put up over there. And these guys actually have periods over 4 days, which is quite bizarre. How do you make a contact binary that has, it's so inflated that it has an orbital period of 4 to 6 days, and that is something we can't quite explain. What's also important to consider is that these 3 systems here have detected tertiary companions, not the others. So is there a role of the triple star, the 3rd star, on the evolution that had happened before or is still happening? And would that explain the widening of the orbit? We don't know. So the widest binaries cannot be explained by the model grids at all. Now let's come back to the last point here, which is the binaries that are approaching contact. As I'd mentioned, does that change that was one point, right? Do the unequal mass binaries originate from systems that are only approaching contact, not the ones truly and deeply in contact? Well, actually, that may be true. The top panel there is it's just for the entire grid by considering systems which are truly in contact. But the second one shows you systems which are just approaching in contact. And the way I define that, which is a bit of an arbitrary definition, but based on the error bars that we have from observations, is a near contact binary is a system where each star overflows its Roche lobe between 90 to 100%. Okay, so that is a bit arbitrary, but it's just to see how things pan out, how that would affect the distributions. So for the Milky Way in particular, the middle panel, you can see that the unequal mass binaries are favored when we consider these approaching contact binaries. And again, the orbital periods also shift towards larger values. And that's how it pans out over here in the 2D histogram. Quite a nice agreement there, except for the widest binaries one more time. But you can see that the period and mass ratio distribution are more in agreement with the observations when you consider also the near contact binaries. Another point to know is that the widest binaries over here are also the most evolved binaries, which is also quite interesting. So aside from the tertiary companion, these are the most, some of them are actually coming very close to TAMS, the end of the main sequence. The rest are all close to the zero-age main sequence. That's another interesting correlation between the widest binaries, but we really don't have an idea of what's going on in them. Almost the last point I would like to share is a recent result. It's a paper that I'm working on with an observer called Michael Abdulmasih. He's an ESO fellow at Chile. This data is something that we've just about obtained last year. So what Michael did was to go through archival data for a few of the contact binaries, which he could get his hands on. And then he derived the P over P dot value for these systems. So what I did was to construct the same 2D histograms to see what we get from theory. Immediately you see there's a jarring distance between the predicted value and the observed value of this parameter. What this parameter tells us actually is the time scale of the mass transfer happening in the binary at the moment. Nature seems to tell us that it's very close to the nuclear time scale of the corresponding to the mass of these binaries. But according to the models, it's 100 times more than that, which is not good. It is not in agreement with what the data tells us. And of course, again, the fact remains that these are unequal masses, but it's also important to know that the most stable configuration for closed binaries is expected to be an equal mass one. That's the least energy configuration for stable for a binary system. And that was actually worked out by a paper of Adams in 2020. So it is interesting that the contact binaries that we observe, majority of them don't have equal masses. Models require them to do. What might be the reasons for that? And there is a link again from this new observation to that point as well. Just to go back a little bit to explain why we have such large values in P over P dot is because, so that is the highlighted portion here in this diagram. And that goes back to the question that Ilya asked, which is the rate of mass transfer. You can see that during contact, all this, the red portion in these lines actually, these are two different models. Values don't matter, but just look at the values to which the mass transfer during contact drops. It goes down to 10 to the minus 10, 10 to the minus 8, which is quite low. And that is due to the implementation of, or the requirement of the mass transfer scheme during contact that is in MESA at the moment, which explains why the mass transfer timescale during the contact phase is much larger than the nuclear timescale of the systems themselves. Upcoming work is that I'm currently doing is actually to look at the correlation between the rotational velocities of some of the observed contact binaries and compare it with the abundances. the nitrogen abundance, of course, is a main tracker of the efficiency of rotational mixing. I don't want to go into interpreting any of this at the moment because I'm still studying it myself. But up top, we can just say that on the outset, there is a seemingly nice agreement between the predicted distribution and the observed ones. But we have to still work out, the origin of these surface abundances. Is it because of mass transfer prior to entering the contact phase or due to rotational mixing efficiency? That is something we have to work out. So to conclude, the lowest mass binaries in the contact scheme, they're quite well observed. The comparison between the theoretical distribution and the observed ones, there is an agreement. We find a strong correlation between the current orbital period and the total mass of the system. Widest binaries come from the most massive ones. Almost all of the confirmed true contact binaries do have equal masses, but the majority of them don't. What is the reason for that? That is something observers will have to inform us. Of course, for that, we need more data as well. So this is a plea for more data on the stellar parameters of contact binaries. For the metallicities that we've considered, the relation between P and Q and total mass is not really affected so much, but the inclusion of these near contact binaries does impact the distributions. Many other things that we, of course, don't consider. I mentioned the energy transfer. We don't know how that might affect the PQ distributions. Too many contact binaries expected with Q equal to 1, not seen in nature. The role of non-conservative mass transfer is something we haven't taken into account. That might be work for the future. The role of tertiary companions, also not considered. And again, more data is required to answer all these questions. And with that, I will end the talk. Thank you very much.
Thank you very much. Yeah, that was a very thorough study of these overcontact binaries. Does anyone have any questions? Ilya?
Hi, thanks for the very nice talk. Sorry to jump in again. I actually had 2 questions. So one was a question about your initial conditions. I was curious how sensitive you are in your population predictions to the choice of initial conditions, because obviously there have been some alternative initial conditions suggested, such as those by Maximo and Rosenda Stefano. But I would be particularly worried about initial conditions for things leading to overcontact binaries, because I would think that these things would then have to be over contact already in some cases pre-main sequence. And so there are some interesting questions about what happens then even before the start of the main sequence, the parts you're not simulating here in your MESA models, perhaps such as interactions with accretion from the surrounding gas from the molecular cloud and so on. Sure. And so to what extent do these things actually impact your initial conditions and distributions? And I guess my second question, I'll ask later.
Yeah, so, I was just about to answer the first one. So even your first one, I'll take it into 2 parts. One is regarding the priors, correct, that are placed, whether changing a flat distribution log P or in Q would affect the final distributions we observe. Is that quite correct?
Indeed, and in particular, whether as Max and Rosenda have argued based on observations, whether it gets messier because, for example, it's not a separate distribution in P and Q, but it's a combined joint distribution in P and Q. So your P's are conditional on your Q's or vice versa. Right.
So I did not consider the combined distribution of P and Q, but I did change the, so these are very simple laws, right? It's a proportionality relation. So I changed the exponents on them to see how that might affect the distributions. And it seems to be that changing the power of the power law does not really significantly impact the predicted distribution. Now, another thing I want to mention is that the data that Uksan has collected starts with the periods of 1.1 days or so. We don't really know what the priors might be on periods that are lower than that. So to just be on the safer side, we assume a flat distribution in log P. So that's the reason for that choice.
Okay, as I said, I think that makes sense. I would just be worrying about, the things that are not being modeled here at all, that go into setting up the conditions, and to what an extent they can impact things like, things that happen pre-main sequence. My
Right.
second
So
question,
just answering the pre-main sequence part, it's that you're right in that we do start from the zero-age main sequence, assuming that these binaries have made it through the pre-main sequence. That is an assumption that we make as well. And even the pre-main sequence evolution of massive stars is quite dicey. We don't really understand that thoroughly. But just to be systematic with our study, we assume the starting point to be of the evolution, assuming that both stars are on the zero-age main sequence when they start their journey. So that is an assumption we make for making sense of the grid to understand it systematically.
thank you. And my second question was a very basic question. So you had shown these, a nice cartoon of what these stars look like, and they look very non-spherical. And so my question is, is a 1D model really appropriate for treating things which are so non-spherical? And should we be worried altogether that the way that we're describing the evolution of such strongly perturbed stars in codes which assume spherical symmetry is inevitably doomed to fail because it's just a non-spherical problem? Or is it the case that somehow all the important things are happening in the core, which is still roughly spherical, and so on?
Well, see, these stars are driven by nuclear expansion, right? So that is an important thing to consider. And secondly, for the study that I have done, which is we're only looking at the orbital evolution, so the period and the mass ratio, the non-spherical aspect of the problem, I am not so sure what its impact might be on the orbital period and the mass ratio itself. Where that can come into play would be the mixing that's happening in the stars. That is something we are not so sure about. Using only rotational mixing might not be sufficient the way it's implemented in the 1D code. So other forms of mixing might come into play. And that might will in fact change the nuclear abundances on the surface, the luminosity and effective temperature, things that I've not yet studied thoroughly. But that would be my answer for that.
Thank you.
Thank you. Are there any other questions? I also have a few, but maybe
Please.
I'll ask some of them. So, sorry, I might have missed your explanation, but in your figure, it looks like with higher metallicity, you have a higher period. What was your explanation for that?
I didn't explain that actually. So I was hoping that would come as a question. Thanks. So actually, it's quite a basic one, right? So at higher metallicities, stars are born with larger radii for the same mass. So at lower initial orbital periods, they end up merging. So those ones vanish from the distribution. And that's why there's a shift in the orbital period overall, because the lower ones end up merging for higher metallicities.
Okay. Oh, okay. Yeah, okay. So it's not like, there's nothing to do with the winds then, because I thought.
Not at these values, not quite.
Yeah. And so my other question was, so you have this mass transfer rate formula that I can understand why you want to use some like the functional form you have to make the stars towards, like, you want to go towards the mass ratio equals 1, but how is this functional form actually like calibrated?
Okay, so
I mean, it could be any function, right? As long as it goes to 0 at q equals 1.
Right. So for that, actually, what Pablo did in his work, in his PhD work, was to consider the equipotential surfaces for L1 and L2 for different masses, and then he derived an analytic expression for this for approaching during contact, rather, based on certain masses and radii that he looked at. So I would really recommend you go to his thesis to read that in more details in one of the appendices there. But you're right, it could be anything else as well, as long as we can drive the mass ratio towards 1, because that's what we would expect a stable configuration like this to attain. Yeah, but the implementation of that, of the contact scheme, and rather consequently the mass transfer rate, you can see there's the, two orders of difference between what we see in nature and what we have in the scheme itself. So indeed, that's very relevant as to how the scheme is constructed.
Thank you. Yeah, are there any other questions from the audience? Yeah, I also had another one.
Yeah, please.
If it's fine. So you mentioned the possible effect of non-1D-ness on the mixing. And I was wondering, like, because you have a different tidal force acting, like in the contact side and the back side, might have an asymmetrical distribution of elements, but also when you observe these stars are significantly gravity darkened, and they have a different brightness on the back side and the front side and stuff.
Yeah.
When you plot the luminosity on the HR diagram, where is this luminosity measured?
That's a good question, actually. So that's really important, because the data that I plotted here, it starts off, I think the oldest system came from a paper like 25 years, even from the 60s or 70s, so over 40 years. And at that time, I think they just did some sort of a bolometric averaging. But today with Ilksana and Michael, they have devised a 3D sort of 3D model, which takes patches of the star and therefore considers, gravitational limb darkening. And then they add up all those patches to get a complete luminosity of the system, of the two stars. But again, it's such a weird configuration, right? Is this one star, two stars? Does it make sense to think of two different luminosities because they share a surface? It's an open question. I don't know how to answer that.
Yeah, I mean, if you have two different temperatures for the stars in contact, it kind of doesn't make sense, right?
Yeah, so you see here, to answer your question, most of them have the same temperatures. So the circles, the empty circles are the secondaries, and the filled circles are the primaries. So they are very close to each other. They're almost equal in temperature, a little bit different in luminosity. So, yeah.
Yeah. I mean, if there is a temperature gradient, there's supposed to be a flow going from higher to lower. So
that's right. That's right. Yeah.
Interesting. Yeah. So if there's no other questions, we have reached the hour. So let's thank our speaker again.
Thank you.
And thank you very much for the nice talk. And I'll see everyone next time.
Yeah, thanks for the opportunity. Thanks for inviting me to give the talk. Thank you.